College of Engineering and Technology from Department of Civil Engineering. So this is our final year civil engineering subject, 7th semester. So our subject title is CE 8703 Structural Design and Drawing. I'm Michael Devadurai, Assistant Professor. So now we can see about the flat slab and bridges. Unit 2, flat slab and bridges. So see our syllabus: design of flat slab with and without drop by direct design method of IS code, then design and drawing, then IRC specifications and loading, then RC solid slab bridge, then steel foot over bridge, then design and drawing. Then in this unit our course outcome is design and draw reinforced flat slab as per code provisions. So flat slab. So flat slab is a reinforced concrete slab supported directly by concrete column without use of beams. So flat slab we can different types. The first one is the flat slab without drop and flat slab with drop. So see the diagram. So first one is the flat slab plate. So column the slab. So flat slab with column capital. This is the flat slab with column head. So see the third diagram, flat slab with drop. So the drop will be provided between the slab and column head. So this is the portions of column head and drop panel and flat slab positions. So this is the supported columns for flat slab without drops. So see the figure A, flat slab without drop. This is the construction site, so directly taken from the photos. So see that this is the flat slab without drop. So see the figure B, flat slab with drop. So you can see the difference, flat slab without drop and flat slab with drop. You can understood. So this is one building. So figure A and B. The cross section we can mark as the span to span distance, 4 to 4 height distance. So the top of our flat slab view is the, we can split into panels. Okay, we can split into panels by square shapes. So design an exterior panel of flat slab floor system for a warehouse 24 meter and 24 meter divided into panels of 6 meter into 6 meter. So live load is equal to 5 kilonewton per meter square. Then column size is equal to 400 mm diameter. So this is given as a diameter. So the column is a circular positions. And M20 grade concrete Fe415 HYSD bars. Then height of story is 3 meter, is nothing but floor to floor height. Then thickness of slab is column strip is 300 mm and thickness of slab and middle strip is 220 mm. So this is our diagram. So we can split into 24 meter and 24 meter, split into 6 by 6 panels. Okay. So step 1, dimensions of flat slab. So thickness of slab in column strip is equal to 300 mm is given in our question. So thickness of slab in middle strip is equal to 200 mm. This is also given in our question. Then column head diameter is equal to 0.25 into L. This is our formula. So L is the panel size. So 0.25 into 6 meter. So is equal to 1.5 meter. Then length of drop is equal to L by 3. So this is a formula. So L is equal to span length. So 6 by 3 is equal to 2 meter. Then drop width is equal to 1.5 into 2. So is equal to 3 meter. Then column strip is equal to drop width is equal to is also 3 meter. So middle of width. So width of middle strip also 3 meter. Because the drop width is equal to column strip. So column strip is equal to width of middle strip. So step number 2, stiffness stipulations. So stiffness of column is equal to Kc is equal to 4 EI by L. So 4 is a constant, E is the constant. So I is equal to D power 4 by 64. So D is the diameter of column. So diameter of column is given in our question 400 mm. Then divided by 64 into 3000 is the L value. So L is the 3000 mm. then 1.67 into 10 power 6 into E. Then column both at the top and bottom, so Kc is equal to 2 into 1.67 into 10 power 6 into E. Then stiffness of slab is given by stiffness of slab Ks is equal to 4EI by L. So 4 is a constant, E is the constant. So next I is equal to B dq by 12. So B is the 6 meter, so 6000 mm is the panel size. So 3 is the width of the column strip, so 300 mm. So B d cube divided by 12 into 6000 is the panel size, so 6000 mm. So is equal to 9 into 10 power 6 into E. So from our IS 456 2000 page number 56, alpha C formula is there. So alpha C is equal to Kc by Ks. So 2 into 1.67 into 10 power 6 E divided by 9 into 10 power 6 E. So alpha C is equal to 0.37. Then IS 456 2000 page number 56, table number 17. So ratio is there. So ratio L1 by L2 is equal to 1 by 1 is equal to 1. So AC minimum is alpha C minimum is equal to 0.7. Then step number 3, find load. So live load is equal to given in our question 5 kN per meter square. Then dead load is equal to 0.5 into 0.3 plus 0.2. So 0.3 is the thickness of middle strip. So 0.2 is the thickness of middle strip and 0.3 is the thickness of column strip. So into unit weight of concrete is 25. So 6.25 kN per meter square. So floor finish is 0.75 kN per meter square. So floor finish is assumed up to 0.721. Sometimes they will be given in our question. So total load W is equal to add live load plus dead load plus floor finish is equal to 12 kN per meter square. So factor load is nothing but, so 12 into 1.5. 1.5 is the factor load. So multiplied by that total load. So 12 into 1.5 is equal to 18 kN per meter square. The step number 4, find bending moment. So these values are taken from our IS 456 2000 page number 55. So total moment M is equal to W into Ln divided by 8. This formula from our code book. So Ln is equal to clear span. So we need to minus the half of the width of the column strip. So 6 is the panel size. So 6 minus 1.5. So our width of the column strip is totally 3 meters. So we need to minus the half of the column strip. So 3 by 2 is equal to 1.5. So 6 minus 1.5 is equal to 4.5 meter. Then W is equal to WU into L2 into Ln. So this also from our code book IS 456 2000 page number 55. So 18 into 6 into 4.5. So 486 kilonewton. So total moment is equal to W L by 8. So W is equal to 486 into Ln is equal to 4.5 meter divided by 8. So moment is equal to 274 kilonewton meter. So interior negative design. So this also formula from our code book. So IS 456 2000 page number 55. So is equal to 0.75 minus 0.1 divided by 1 plus 1 divided by alpha C into M. M is the moment. So all the values are, if you already know alpha C is a known value, so moment is a known value. So all the values directly apply in that formula, you got the answers. So interior negative design is equal to 194 kilonewton meter. Then interior positive design, this formula also same pages. So 0.63 minus 0.28 divided by 1 plus 1 divided by alpha C into M. So M is the total moment. So interior positive design is equal to 141 kilonewton meter. So exterior negative design, so we have one formula 0.65 divided by 1 plus 1 divided by alpha C into total moment. We know the alpha C values and the moment values, so apply the values, you got a 73 kilonewton meter. And the interior negative design column strip is equal to 75% into M. M is the moment, so 70% is 0.75 or 75 divided by 100, anything you can write to it. So M is equal to 194, this is a moment value. So our column strip interior negative design is 146 kilonewton meter. So middle strip is the remaining 25% is the middle strip value. So 0.25 into 194. So answer is middle strip moment is equal to 48 kilonewton meter. So exterior positive design. So column strip is equal to 60% of moment. So 60% is 0.6 into 141 is equal to 85 kilonewton meter. Then middle strip is equal to remaining 40% of that total moment. So 40% is 40 divided by 100 or 0.4 into 141 is equal to 1. Middle strip is equal to 56 kilonewton meter. So exterior negative design is equal to column strip is equal to 73% of moment. So 75 into 73, 0.75 into 73 is equal to 55 kilonewton meter. Then middle strip is equal to 0 because this is the exterior negative design. So X is the after that column slab. So here that place will not be provided any middle strips because the middle strip will be provided between the two columns only. So step number 4, check for thickness of slab. So we know that formula D is equal to root of mu by 0.138 FCK into B. Then thickness of slab near drop column strip. So D is equal to moment values we know that 146 into 1046 will be 0.138 into 20 into 3000 is equal to 133 mm, and thickness of slab middle strip. So D is equal to apply the middle strip moment value. You got the answers. D is equal to 83 mm. So thickness of slab near drop middle strip. So overall depth capital D is equal to 300 mm and small d is equal to 300 minus 30. So 30 is the cover slab for flat slab. Okay, 30 is the cover slab for flat slab. So D is equal to 270 mm. So thickness of slab middle strip. So overall depth D is equal to 200 mm. So small d is equal to 200 minus 30. So 200 minus 30 is equal to 170 mm. So step number 5, check for shear stress. So total load on circular area. So W is equal to pi by 4 into D plus D the whole square into WU. So D is 1.5 meter width of the column strip. Then D is equal to 0.27. This is the effective depth of the slab, the whole square into 18. 18 is the load. So is equal to W is equal to 44.3 kilonewton. Then shear force is equal to total load minus load on circular. This is one formula. So total load is one note W into L into L. L into L means panel size. L into L. So W is the load. So 18 into 6 into 6 minus total load on circular means 43.3. So previously we have find out W. So shear force is equal to 603.7 kilonewton. Then shear force per meter of perimeter. So perimeter is nothing but column head diameter plus depth ratio. So 603.7 divided by column head diameter is 1.5 meter plus effective depth is 0.27 because 270 mm. So shear force per meter is equal to 340.66 kilonewton. So shear stress tau V is equal to shear force by BD, area of cross section. Okay, this is one formula for shear stress, load by area. So the load is a 341.07 into 10 power 3 divided by B is equal to 3000 mm because the width of the column strip, and D is equal to 270 mm, the effective depth. So shear stress tau V is equal to 0.42 Newton per mm square. Then permissible stress K is into tau C. So K is equal to 0.5 plus beta C. So this formula is taken from our code book page number 58 and 59, IS 456-2000. So beta C is equal to L1 by L2. So beta C is equal to L1 by L2. So L1 is nothing but the panel size. Okay, panel size 6 meter into 6 meter. So 6 meter is taken as a L1. The another one side is L2. So that's also 6 meter. So beta C is equal to 1. So K is equal to 0.5 plus 1. So our answer is 1.5. So this is above 1 meter. So we need to check the another step. So tau C is equal to 0.25 into root of FCK. So FCK is given in our question 20. So tau C is equal to 1.118 Newton per mm square. So permissible shear stress equal to Ks into tau c. So Ks is the 1. So tau c is 1.118. So finally permissible shear stress is 1.118 Newton per mm square. So this value is greater than shear stress value. So hence safe. So step number 6, find reinforcement for column strip negative bending moment. So m is equal to 0.87 Fy AST into D, 1 minus AST into Fy BD into FCK. So this formula is taken from our code book IS 456 2000 page number 96. So this formula apply the moment values 146 into 10 power 6 is equal to 8, 0.87 is the constant value, and Fy is the Fy 4 and 5, then AS is the constant and D is the effective depth for slab, then 1 minus AS into Fy. Fy is the 4 and 5 given in our question. So B D into FCK, B is the 3000 mm because the width of the column strip, and D is equal to 270 mm and FCK is equal to 20. So it will be given in our question. So finally you got a one equation mode. So using calculator, go to mode position, then equation, then degree, then second order degree. So sometimes the AST will be found by third order degree. So in this question we have enough for the second order degree. So A is equal to 2.49, then B is equal to minus 97.48 into 10 power 3, and C is equal to 146 into 10 power 6. So x1 and x2 values are given. Then AST for per meter is also there. So provide 12 mm dia bars. Spacing is equal to, we know the spacing formula, 1000 into by d square by 4 divided by AST. So the area is 475.33. So D is the 12 mm. So spacing is equal to 237.93. So we can round it as 240 mm. So provide 12 mm dia bars at 240 mm center to center distance. Then find distribution reinforcement. So distribution reinforcement is nothing but this is a AST minimum. So AST minimum is equal to 0.12 by 100 B into D. So 0.12 by 100 B is equal to 3000 mm into D is the overall depth of the slab, so 300 mm. So AST is equal to 1080 mm square. So we need to find out the per meter. So divided by 3. 3 is the width of the column strip. So per meter is equal to 360 mm square. Then we need to spacing also, find the spacing also, minimum distribution reinforcement. So provide 10 mm dia bars. So spacing is equal to the same formula, 1000 into by d square by 4 divided by AST. So AST is the 360. So spacing is equal to 218. So rounded as 220 mm. So provide 10 mm dia bars at 220 mm center to center distance. So for middle strip, so negative and positive bending moment. So M is equal to the same formula. So this formula is taken from our page number 96 from IS 456 2000. So moment only will be changed in this step. So remaining all the values are same because of all the values are same as this slabs, middle strip and column strips. So this is for middle strip. So we can take in the middle strip moment. So middle strip moment is 55 kN meter. So apply the 55 into 10 power 6 kN meter. So using calculator, then A values, B values and C values are applied in equation mode. You got two x1 and x2 values. Take the least values for AST. So AST is equal to 229.08 mm square. Then find the spacing values. Provide 12 mm dia bars. So spacing is the same formula for the previous. So apply the D is equal to 12 mm, then AS is equal to 229. So you got a 493.70 mm. So we can round it as we didn't take the spacing value above 300 mm. So take 300 mm or below 300 mm. So provide 12 mm dia bars at 300 mm center to center distance for both positive and negative moments. Then find distribution reinforcement. So AST distribution is equal to 0.12% of cross section. So 0.12 divided by 100 into 3000 mm into 200 mm. 200 is the overall depth of the middle strip. Then AST is equal to 720 mm. So we can convert into per meter for this AST. So apply per meter is equal to 720 divided by 3. 3 is the width of the column, so is equal to 240 mm square. So provide 10 mm dia bars. So we know the spacing formula, so apply the diameter values is the d is equal to 10, then apply AST values also 240 mm. So you got a 327 mm. So provide 10 mm dia bars at 300 mm center to center distance for both positive and negative moments. Then step number 7, check for deflection control. So PT is equal to 100 AST divided by BD. So FA is equal to 0.58 into 415, 240.7. So modification factor is equal to 1.8. Then L by D max is equal to modification factor into 26. So 1.8 into 26. The modification is 1.8. So 1.8 into 26. So this modification factor taken from page number code book IS 456 2000, page number 35, 36, 37 and 38. Check the 4 pages. You can some of the graphs are there. So in difference between PT and FA, what is it? You got a modification factor 1.8. So L by D maximum is 46.8. So L by D provided is equal to span by depth ratio. So span is equal to 6 meter. So apply the 6000 mm. Divided by depth is equal to 170 mm. So L by D provided is equal to 35.2. So L by D maximum is greater than L by D provided. So hence safe. Thank you.